Hi everyone, so today we're going to talk about De Moivre's theorem and roots of unity. So De Moivre's theorem has a lot of really beautiful applications in the world of complex numbers, and one of them is the roots of unity. So from this De Moivre's theorem, we can actually find out a closed form for all of the complex roots of unity, right? So we're going to see what the relation between these two quantities are, and yes, let's just get right into this video. This is the problem number 6 from the AIME in the year 2012. And in this video, we're going to be talking about De Moivre's theorem, and I'm also going to give you a rough proof of it, Euler's identity, of course, and then we're going to talk about how we can derive the nth roots of unity from De Moivre's theorem. So the nth roots of unity, I may have discussed this before, as a closed form, so you can actually figure out all of the nth roots of unity other than obviously one is obviously a root of unity. Other than that, the complex roots of unity, you can figure it out, the closed form for that using De Moivre's theorem. Then obviously we have book sessions for AIME, and at the end a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So let's go through this question, and they are saying that the complex number z and omega satisfy this given equation. So z raised to the power 13 is equal to omega, and omega raised to the power 11 is equal to z. Now the imaginary part of z is the sine m pi by n for relatively prime integers m comma n blah 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 with m less than n, and find n. So basically it's essentially saying that the imaginary part of z is equal to sine m pi by n, and then we need to find out the value of this n. Right? As simple as that. So really it has not much to do with this omega, right? This omega is really just an interstitial variable, interstitial complex number. It's not giving us much help over here. Essentially at the end of the day we need to deal with the complex number z, right? So I can take this value of omega and plug it in over here, right? So z raised to the power 13, which is omega, raised to the power 11, and then we get back z. So 13 times 11 is 143, so z raised to the power 143 is equal to z. Now since z is non-zero, I'll get z raised to the power 142 is equal to 1, obviously by dividing z on both sides. So this is quite fascinating, and it's clear to see that we are considering 142 roots of unity. So one of them will obviously be z equal to 1, which is the real root of unity, and there'll be 141 other complex roots of unity, which is very fascinating, right? Quite a big number of them. So before we deal with how we can work with these 142 roots of unity, before we go on to that, let me just maybe talk a little bit about this De Moivre's theorem, right? So De Moivre's theorem. So this guy was a French mathematician, I believe, and he gave this really cool looking theorem, and it essentially states that cosine theta plus I sine theta raised to the power n is equal to cosine n theta plus I sine n theta. So whatever n we have in the exponent really gets distributed out here in the angles. That's essentially the core concept of it, and the proof is actually very simple. The proof is very simple. We can easily prove it using Euler's identity. So cosine theta plus I sine theta can be written as e raised to the power I theta. Now if I just raise this to the power n, so cosine theta plus I sine theta raised to the power n becomes e raised to the power I times n theta. And again, from Euler's identity, I know that e raised to the power I times n theta is nothing but cosine n theta plus I sine n theta. So basically from these two expressions, I can essentially see that this and this are equal. So cosine theta plus I sine theta raised to the power n is equal to cosine n theta plus I sine n theta. Right? So it's as simple as that. Right? Easily provable using Euler's identity, but effectively just maybe keep this in the back of your brain. Don't ignore this just because it is trivial by Euler's identity, and once you can convert it into polar form, it gets easier. No, maybe just keep this in mind because it has some very beautiful applications. One of them is the roots of unity, right? So let's talk a little bit about the roots of unity. So what exactly is this roots of unity? Like we were saying before, like z raised to the power n is equal to 1. So these are the nth roots of unity, and obviously one of them will be z equal to 1, but then you will have n minus 1 complex roots of unity, which is what we're going to talk about. Z is equal to 1, well, it's a simple trivial root, obviously, but a better discussion will happen on how do the complex numbers look like, how do the complex roots look like, right? So Z is equal to 1 raised power 1 by n, obviously taking the nth root on both sides. Now 1, I can write it as cosine 0 plus I times sine 0, because sine 0 is 0 and cosine 0 is 1. So I can write 1 in this manner. So a real number can be represented as x plus iy as well. Not bad, isn't it? So then Z becomes cosine 0 plus I sine 0 raised to the power 1 by n, just representing 1 with this form. Okay, awesome. So, well then Z becomes cosine 2k pi plus 0 plus I sine 2k pi plus 0 raised to the power 1 by n. Because really, using the concept of allied angles in trigonometry, you know that whenever you add an integral multiple of 2 pi, it does not change. Right, so at 360, at 720, these values, they do not change with one another. So you can really add 2k pi without having any change in the expression, right? So then Z essentially becomes cosine 2k pi plus I sine 2k pi whole raised to the power 1 by n. And from De Moivre's theorem, if you remember De Moivre's theorem, like I said before, the exponent gets distributed in the angles. So Z becomes cosine 2k pi by n plus I sine 2k pi by n, essentially applying De Moivre's theorem. So therefore, Z raised to power n is equal to 1 has roots that look like Z is equal to cosine 2k pi by n plus I sine 2k pi by n, where this k runs from 0, 1, 2 all the way up till n minus 1. So like I said, we'll have these n values, and k obviously runs from 0, 1, 2 all the way up till n minus 1. So this expression 0 power n is equal to 1, this will obviously have n roots, and they look something like this. So you keep on plugging the values of k. First you put 0, 1, 2, 3, 4, so on and so forth, and then you'll get n roots, and it's easier to see that at k is equal to 0, we get Z is equal to 1, which is obviously the trivial root or the real root of this expression. And then you'll obviously have n minus 1 complex roots, right? So this is essentially the closed form of the roots of unity, right? So Z raised to power n is equal to 1. This essentially implies that Z is equal to cosine 2k pi by n plus I sine 2k pi by n. This is how Z looks, and k obviously runs from 0, 1, 2 all the way up till n minus 1. This is essentially the crux of what I want you to remember. And this is the closed form of our roots of unity. These are how the n roots of unity actually look like, right? So coming back to a question, in our question we had where did it go? We had 142 roots of unity, right? So we had Z raised to the power 142 is equal to 1. Now in this expression Z raised to power n is equal to 1, I just need to plug in n is equal to 142, right? And when I do that, I'll get Z is equal to cosine 2k pi by 142, just n is equal to 142 plus I sine 2k pi by 142, right? So maybe if I just simplify this a little bit, Z is equal to cosine k pi by 71 plus I sine k pi by 71. Now in the question, what had they given to us? K pi by 71. Right? In the question that they have given to us, that the imaginary part of Z is actually m pi by n. Right? They had given to us that the imaginary part of Z is equal to m pi by n, and we had to find the value of n. Well, now it's pretty trivial. This is Z and this is imaginary part. So just compare, k becomes m and 71 becomes n. So therefore our answer is n equals to 71. So this was actually a rather easy question if you had actually known this statement, or this theorem, or this result, that these are how the complex roots of unity look like. You just really had to plug in n is equal to 142 and that's it, you're done. So if you had known this De Moivre's theorem, if you had known how these roots of unity look like, this is actually a gift for you. This is actually like free marks. This is bonus marks. And this is pretty easy to do if you had the knowledge of this De Moivre's theorem. So if you're preparing for these American examinations, AMC, AIME, or whatever they might be, the knowledge of complex numbers is really, really helpful. And I hope you learned a little bit about that from here today. Okay, so we have certain book sessions for USAMO, JMO, and AIME. Elementary number 3 by David Burton. Problem solving strategies by Arthur and Gell. functional equations by Venkatachala, problems in plane geometry by Sharikin, elementary number theory by Sierpinski, graph theory Harari, and combinatorics by Brualdi. Okay, so we have a similar but challenging problem, and this is essentially telling us if 1, x, y, and z are the distinct fourth roots of unity. So we have z raised to power 4 is equal to 1, and these 4 are obviously the roots of unity. X, y, and z will without a doubt be the complex roots of unity. Find out the value of this expression, right? Pretty interesting question, although it might not be very hard to do, but try it out, and if you're able to do it, let me know. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.